Okay, we're back. In the previous video, I showed you one method for calculating the theoretical yield in a limiting reactant stoichiometry problem. Now I'd like to show you another way, which is what I call the calculate the theoretical yield twice method. Here's our reaction again. Iron 3 chloride reacting with potassium carbonate to form a precipitate of solid iron 3 carbonate and potassium chloride in solution. If you recall, we started out with 10.00 grams of iron 3 chloride and 15.00 grams of potassium carbonate. This method simply has you calculate the expected yield of iron 3 carbonate twice, once starting with each reactant, and compare them. So I'll take my 10.00 grams of iron 3 chloride, divide by its molar mass, 162.20 grams per mole. Multiply that by the mole ratio, 1 mole of iron 3 carbonate expected for every 2 moles of iron 3 chloride, and then convert moles of iron 3 carbonate to grams of iron 3 carbonate by multiplying by the molar mass, 291.73 grams per mole, gives me a yield of 8.993 grams of iron 3 carbonate. We'll do that again, this time starting with the mass of the other reactant, potassium carbonate. 15.00 grams of potassium carbonate over 138.21 grams per mole, multiplied by the mole ratio, 1 mole of iron 3 carbonate for every 3 moles of potassium carbonate to give us moles of iron 3 carbonate, and then multiply that by the molar mass, 291.73 grams per mole, gives me 10.55 grams of iron 3 carbonate. So calculating the theoretical yield with each of the initial masses of reactants gives me 2 different answers. Which is the correct one? You're right, the smaller one. Okay? The smaller one is the correct answer, and that tells me that iron 3 chloride is my limiting reactant. So simply by doing these 2 successive calculations, I've been able to answer both questions. Number 1, what is the limiting reactant, in this case iron 3 chloride, and what is the theoretical yield, in this case 8.993 grams. Okay? Well, to finish up the problem, all we need to do now is to calculate the mass of the excess reactant, potassium carbonate that's left over. I'll simply start with the amount of limiting reactant I have and calculate how many grams of potassium carbonate will get used up in a very similar process. So I'll take my 10.00 grams of iron 3 chloride. Remember, once you've identified a reactant as the limiting reactant, everything else after depends upon that. So I'll convert that to moles by dividing by the molar mass. Now I'll figure out how much potassium carbonate is going to get used up while the limiting reactant reacts. So I'll multiply that by the mole ratio. 3 moles of potassium carbonate react for every 2 moles of iron 3 chloride. And I'll convert that to grams by multiplying by the molar mass of potassium carbonate, 138.21 grams per mole. Gives me 12.78 grams of potassium carbonate that actually reacted. What mathematical technique will I use to figure out how much is left? Why, subtraction, of course. 15.00 grams of potassium carbonate that I initially had minus the 12.78 grams of potassium carbonate that reacted gives me 2.22 grams of potassium carbonate left, which, after rounding, is exactly the response that I got before. Okay? So, here are the 2 methods for solving limiting reactant stoichiometry problems. The point is, use whichever one makes more sense to you. If the have versus need method is more intuitively obvious, go ahead and do that. On the other hand, if simply calculating theoretical yield twice, like we did here, makes more sense to you or is somehow less complicated, use that. Okay, bye.